Log on, tune in, find out. Another good idea from Cambridge.
That everybody had left for Easter vacation, but I'm happy to see that there's still a substantial audience. So it's a pleasure to introduce Peter Fiebig, who will tell us about Lusztig's conjecture via moment graphs.
Thank you very much, and thank you very much for the invitation for this talk first, and also for the invitation to the Newton Institute for the program. To start with, let me remind you of Lusztig's conjecture, one of Lusztig's conjectures. So it's a conjecture. I will be talking about the conjecture on characters, simple characters of reductive groups in positive characteristic. So G will denote a reductive algebraic group over K, a field that is algebraically closed, and we can assume that it's connected, almost simple. And simply connected. So then we choose a torus and a Borel subgroup, a maximal torus, and a Borel subgroup, and we denote by X the characters of the maximal torus. So this is a lattice. And our choice of the Borel subgroup identifies the dominant weights here. So these are the dominant weights. They depend on the choice of the Borel subgroup. And for any dominant weight, there is L lambda, the simple G module with highest weight lambda, and we are interested in the structure of these simple modules, the simple highest weight modules. And the first question that one should ask as a representation theorist is the question about the character of such a module. So what is the character? So the torus is a diagonalizable algebraic group. So it acts semi-simply on every rational representation, in particular on this lambda. So for any weight x, we define L lambda mu. For any mu in x, we define L lambda mu to be the set of elements in a lambda on which the torus acts by multiplication with a scalar given by the weight. So let's say T of m, the action of the torus, should be given by the character mu. And we can form the formal character of L lambda as the sum of the dimensions of all these weight spaces as an element in the free group generated by these mu. So the question is, the problem is to calculate these characters. So there's one very classical case which is comparably easy to solve, and it is the case of characteristic 0. So if the characteristic of K is 0, then the classical theorem of Weil states that the character of L lambda is given by the while character. The while character, given by this famous formula. Let me write it down. Afterwards, explain what the symbols here mean. So on the right-hand side here, we have this this expression where W is the while group acting on the lattice X, the while group associated to our group G. The while group L is the length function, and rho is 1/2 of the sum of positive roots. And so it turns out that in this group algebra, here on the right-hand side, this expression is divisible by this one, so it's a well-defined element. And this is the character of L lambda, and the proof is very wonderful, very mysterious. It's just a formal calculation with characters, and this gives the answer to our question in the case that the characteristic of K is 0. So, but the case that the characteristic is positive is much more difficult, and still it's unsolved. So in this case, there's Lusztig's conjecture, which holds, or which is conjectured only for characteristics that are bigger or equal to h, which is the Coxeter number of our group. So, for example, for G SLN, if G is SLN, K then H is N, right? Okay. H is N. So it's a comparably small number, and so this gives a lower bound on the whole theory that is developed by Lusztig and Janssen and Anderson and Zergel and a lot of others. Below this number, everything gets very, very mysterious and very exceptional in a sense. So this is our general assumption, and in this case, Lusztig's conjecture is as follows. First, we have to introduce the affine Y group with an index P, maybe. So the affine Y group. So it's a group of affine transformations on the lattice X, and it's, well, I think I'll come back to the definition of this later, but well, you probably all know what the affine Y group here is in this situation. And let's call let's define for W in the affine Y group and lambda in X, let us define W dot lambda to be W of lambda plus rho minus rho, where again rho is this half sum of positive roots. And let's call W restricted if W dot 0, if 0 is smaller or equal to W dot 0 evaluated at alpha check and still smaller than P for any simple root alpha. So this is a finite set for inside W hat. So W hat is an infinite group, but it contains this finite set of restricted elements. And so Lusztig's conjecture the following: if W is restricted, then the character of the simple module with highest weight W dot 0 is given by the following formula. So you sum over all x in W hat such that x dot 0 is in x plus. And here you have the following expression. So there's a factor -1 to something, to the sum of the length. And then here you have the affine Castaing-Lusztig polynomial evaluated at 1 times the y character that we defined over there. So and here h is the affine Castaing-Lusztig polynomial. And W0 in W, so that's the finite Weyl group sitting inside the affine Weyl group, is the longest element. So this is Lusztig's conjecture, and so far it's not proven. So what we know is that this conjecture is true if P is big enough. So for a fixed root system, for a fixed group scheme, the conjecture is true if P is big enough. And there's also a bound, so we know that it's true if P is bigger than a certain explicit number that you can define, calculate in terms of the affine Weyl group. But this number is still very, very, very large. Okay, so this was the first part of my talk. Wanted to introduce Lusztig's conjecture. And the next part, the second part, is the introduction of affine moment graphs. Okay. So the goal is to write down a very different conjecture, which is in a sense much more elementary and only depends on the underlying root system of the group, which implies Lusztig's conjecture. But which is also not proven in general. So it's a conjecture on certain ranks of sheaves on moment graphs. So let me introduce a moment graph. So a moment graph is a graph with vertices and edges where the edges are labeled by certain elements of a lattice. So in our situation, it's defined as follows. We define G to be the graph with well, I forgot something. Okay. Sorry. First, before we can define the moment graph, we have to linearize the action of the affine Weyl group on X. So the only thing that we remember from the theory here now will be the action of the affine Weyl group on X. But we forget about the group and for the moment also about the field K. So we have this affine group acting on the lattice X, and we linearize this action. We define X hat to be the lattice that we obtain by adding just one additional copy of Z. So and then we can define a linear action of W hat on X hat, and well, instead of writing down the formulas, I give you the general idea. In the case of an A1 root system, so it's a case of a rank 1 root system, you have the affine Weyl group acting on a lattice of rank 1. The affine Weyl group, and it's given by certain affine reflection hyperplanes. So the affine Weyl group is just reflections on all these hyperplanes. And so this is X. And what we do is we add another copy of Z, and we put the lattice inside X hat, but not at the 0 section, but somehow at Z equals 1. And then we draw the linear hyperplanes generated by these affine hyperplanes. And now you can define reflections on these linear hyperplanes, and it turns out you get the same group, the affine Weyl group W hat, that preserves all level spaces here. And here in this level you get the affine action, whereas here, for example, you get an action which factors over the finite Weyl group. Here you see somehow the hyperplanes come together, and you get the finite Weyl group back. So here's an affinization, linearization of the affine Weyl group, and W hat is generated by reflections as alpha n at the hyperplanes H alpha n. So H hat alpha n, these are linear hyperplanes which are given by the following equation. Alpha check plus n delta. So what do I mean by this? Alpha check is the co-root associated to alpha. It's the equation of the reflection hyperplane of the reflection as alpha. And because we are looking at the affine situation, we have all these several hyperplanes here parameterized by n. So alpha here is a root, maybe a positive root, and n is an integer. So what we now have is a group W hat which is generated by reflections, and we have equations for the reflection hyperplanes. And now we can define the graph.
And delta is for the coordinate on Z, right?
Yes. Delta is the coordinate on Z. This is the additional coordinate. So we define the graph G. The graph G, and it has the vertices that are elements of W hat of the affine Weyl group. So any element gives us a vertex and edges. So X and Y in W hat are connected by an edge. if x is S alpha n times y, so if they differ by one of our generating reflections, and the edge is labeled by alpha check plus n delta. So the equation of the reflection hyperplane for S alpha n. So what we now have is a labeled graph, and we give each edge a direction. And it's directed towards y, right, if the length of y is bigger than the length of x. So what we have is a directed labeled graph. So maybe I can give you an example, not of an affine graph, but of one of my favorite finite graphs. Take the other one. Oh, okay. Well, let's see. Do I have to wait a little, maybe?
Possibly, yes.
Okay. 2 second bulb.
Yes.
You might have just blown the bulb.
Oh,
Probably blew the bulb up.
Oh, I'm sorry. I'm sorry that. Okay, well, okay. Oh, thanks. Oh, great. Thank you very much. So I hope you can see this. This is a graph that turns up actually for the finite Weyl group, but also in D-theory, in a representation theory of type A3. It's the first graph that is singular. And I will define what singular means in a second, but so that's a typical such graph. So what we need next is the notion of a sheaf on such a graph.
So this is a subgraph of the moment.
Yes, that's a subgraph of a full moment graph. So the important theory for these graphs is a sheaf theory for these graphs. So for this we have to define choose a field of coefficients. Of course, we take our field that from the first part of the talk, so the ground field of our group, and then we define the symmetric algebra of the vector space of the K vector space associated to our lattice, to the lattice that contains all the labels. So we can now assume that the labels of the okay. Here we need the affinization of the dual lattice. So here we assume that our labels, the labels of the graph, are contained in this lattice, and we take the corresponding K vector space corresponding to this lattice. Then we take the symmetric algebra. Now we can define what a sheaf is. A sheaf on G with coefficients.
You took coroots.
I mean?
So it's coroots, not roots.
Yes, it's coroots. Yes. The labels are coroots. That's It's very important here.
And this K underneath is, S and the K means over the.
This the symmetric algebra over K vector space. So a sheaf on G with coefficients in K is given by the following data, by an S module mx for each vertex, an S module ME for each edge E that is annihilated by the label alpha E times ME should be 0, where alpha is the label. And thirdly, a map rho xe from mx, so a homomorphism, from mx to me for each edge that contains x as a vertex. So this is a kind of maybe unfamiliar exotic data that you can associate to such a graph, but it has a lot of, this definition is very convenient in both topology and representation theory. So this is a sheaf. So you give S modules for each edge and for each vertex. It maps from the two endpoints of an edge, from the two modules on the endpoints to the modules on the edge. Okay, so when there are sheaves, there should also be global sections or sections of such a sheaf, and the definition for a section of such a sheaf is very easy. If I is a subset, then we define gamma I M. So M is a sheaf. Then we can define the sections of M over I to be the following space. We consider the tuples of elements in the direct product of so the tuples of the direct product of these spaces sitting on the vertices on I, with the property that rho xe of mx equals rho ye of my for any edge E that connects x and y. And x and y are elements in I. So what you do is you pick at any vertex, you pick an element of the corresponding S module that is given by your sheaf in such a way that if the two vertices are connected by an edge, the two elements you picked have the same image on the corresponding edge using these maps rho. So it's another definition which might be very exotic, which you might be unfamiliar with. But now there's a natural question, namely, first of all, the definition of a sheaf And also the definition of a section does not depend on the direction of the edges that we chose. But we can use it to try to solve the following problem, namely, we would like to try to construct such sections. And for example, if we take all the vertices, for example in this graph, we could try to construct a global section by beginning at the bottom and choosing just an element at the bottom, and then we try to find solutions of these equations following the directions of the edges. So we pick something here, and then we might pick something here that has the property that these two elements give the same image on a corresponding edge. And so you see, the higher we get in the graph, the more restrictions we do have on the choice of section we can, the choice of elements that are allowed. But there's one sheaf that has the property that that no matter how you construct global sections, you will never find a situation where you cannot extend a local section. So you could. So the problem is the following: suppose we have already a section on such a subgraph, and we want to extend it to a vertex x. Then suppose we have already chosen elements here. Then we have to find an element here in the corresponding S module that maps to the same elements on these edges as the ones below, and this might not be possible, right? For example, if you take the simplest sheaf on this graph that is given by S modules on each vertex and S modules S, and on each edge you take the module which is free of rank 1 over modulo the label, then this graph has the property that you can find sections that are not extendable to these two vertices. And this what makes it singular, this graph, and this is reflected by the fact that the corresponding Schubert variety of type A3 corresponding to this element W is not smooth. So these graphs have a lot of topological and representation theoretic information. So let me now come to these wonderful sheaves, these canonical sheaves that provide universal solutions to these extension problems. So they were first defined by Tom Braden and Robert McPherson in their work on the section cohomology of equivariant varieties. So Braden-McPherson sheaves okay. So we choose W and W hat, and then there is a unique sheaf up to isomorphism BW such that the following holds. First, BW x is 0 unless x is smaller or equal to W, and BW W is the symmetric algebra. So now I should say that S is a graded algebra, and we consider graded modules. So this will become important in a moment. So that's the first property. The second is if E is an edge pointing towards Y, so remember this means that the length of Y is bigger than the length of X, then this map rho XE, which goes from BWX to BWE, is the objective, and its kernel is alpha E times BWX. So here you see if this determines all these modules on the edges once the modules on the vertices are given, and also one of these two maps. And the third property, which is by far the most difficult, is the following. Look at the following maps. We have BWX, which maps to a direct sum of all these BWE, where E is an edge that starts at X. And here we have the direct sum of the corresponding maps. Let's call this map A. And here here we have the direct sum of the Y that sit at the endpoints of exactly these edges. Here we have a direct sum of this rho YE. And here, sitting inside, we have the sections of BW on a certain subgraph. And here we have another composition B. So then the condition is that the image of A is the image of B, and this map A from BWX to the image of B is a projective cover. In the category of graded S modules. So this is a quite technical statement, but if you look at the definition of a global section, and if you think about this a little bit, then this tells you that that any such section on this subgraph can be extended to the vertex X. You take any section here, and then you map this section via B to this element, and then you take a pre-image under the map A, and these maps ensure that the pre-image extends such a local section. Yeah?
What's the order on the vertices? I don't understand. Z?
Right. The order, this is the Brüher order in this case. It's generated by, thank you, by the directions of the edges. Yes. So this is the Brüher order. Okay, so this is the Braden-McPherson sheaf. And from here, from this property, that this is projective cover, this property tells you that BWX is a graded free S module. In particular, if you forget about the grading, it's a free S module, a free module over symmetric algebra. So here comes a conjecture. Oh, yes. Before I state the conjecture, one definition. So far, everything worked quite well independently of the field. But there's one restriction on the field, and this is as follows. We say that Wk, so K is our field, W is the element in the F and Y group, is a GKM pair. And GKM stands for Goreski, Kottwitz, and McPherson. Somehow in their paper on equivariant cohomology and causal duality, this property, I mean, in a very different setting, somehow occurred for the first time. I mean, they only had characteristic 0, but topologic, they had a topological statement which is somewhat equivalent to this one. So what is it? We say that Wk is a GKM pair if for all x and y that are smaller, x, y, z that are smaller to w, and any two edges E that connect x to z and E prime that connect x to y, we have that k alpha E does not contain alpha E prime. Alpha E prime. So what does that mean? It just means that if you, for this subgraph, if you fix one vertex, and if you look at all the labels on the edges that are connected to this one vertex, then each pair spans a two-dimensional vector space. So they are not linearly dependent over K. So this is, given the graph, this is a property on K. So the main conjecture is now that the rank of BWX, these spaces that we get here from on the canonical sheaf, are given by the affine Castern-Lusztig polynomial evaluated at 1. So it's the same polynomial that we had before. If KW is a GKM pair.
What is rank?
The rank of an S module, of an ungraded S module. So this is a graded S module. If I get a grading, and you calculate the rank, so it's a free.
All right.
Yeah, sorry. It's a graded free module, which becomes a free module when you forget the grading, and then there's a well-defined number as the rank. Yeah, and this should be given by the Castern-Lusztig polynomial. So this conjecture cannot be proven.
Yeah, if you don't forget grading, do you go into that?
Yes, if you define it in the right way, this should be the polynomial. I mean, this should be even an equation of polynomials. But this is equivalent. So, okay. So, the funny thing is that this conjecture implies a lot of different conjectures in representation theory.
Is it in some cases?
Pardon?
You know it in some cases?
Yes, I will come to that in a moment. So the theorem, the conjecture implies the Castern-Lusztig conjecture for finite dimensional simple complex Lie algebras and Kac-Moody algebras and symmetrizable Kac-Moody algebra and then it implies Lusztig's conjecture. So the one I mentioned in the first part of the talk. It implies Lusztig's conjecture. And so a research project, which is, I mean, we haven't finished that yet, a research project with Arakawa is that it implies the Feigin-Fraenkel conjecture. The Feigin-Fraenkel conjecture is about the characters of simple modules in the critical hyperplane of an affine Kac-Moody algebra. So there's a very similar conjecture, which is similar in a lot of senses to these Kashtan-Lusztig and Lusztig conjectures. And our goal is now to show that this conjecture also implies the Feigin-Fraenkel conjecture. So theorem, the conjecture holds if the characteristic of the field is 0. And the proof is very, very difficult. I mean, maybe in the last 5 minutes I can say a little bit about the proof, but you need topology of the affine flag variety or the affine Grassmannian for this. So the idea is that these spaces BWX, you show that these spaces BWX are given by the local intersection cohomology of Schubert varieties, and then you use a theorem of Kashtan-Lusztig, tells you that those are given by the corresponding Kashtan-Lusztig polynomial.
Excuse me.
Yeah.
I mean, maybe ask a stupid question. This conjecture was when the characteristic was positive.
Yes.
And when the characteristic is 0, you have the Weil formula.
Yes.
And the conjecture is true, so what is the relation with the conjecture?
Right. I think the Weil formula can be viewed as a limit of the Lusztig conjecture. I mean, if P grows, I haven't told you how the affine Y group acts, but if P grows, somehow you get the dominant chamber becomes the fundamental alcove, which means that in a sense it's a limit of the Lusztig conjectures. But I mean, I don't know yet a direct connection between this sheaf theory and simple representations of a group in characteristic 0, if this was your question. I haven't constructed, I mean, I'm not sure if that can be done. But this, at the moment, it doesn't give a new proof of the Weil character formula. Okay. So it holds in characteristic 0, and then because this algorithm of Braden-McPherson is somehow algebraic and finite, you can immediately say that it also holds in characteristics which are big enough. Because if you construct these sheaves over, say, the rational numbers, you end up with only finitely many places where you need denominators. And you have to exclude all prime components of these numbers, and you get that the conjecture also holds once these prime numbers are excluded. So this immediately tells you that it's also true if the characteristic is big enough. But well, you can also give a bound. I don't write down bound because it would need too much definitions and annotations. So let me just say that given W, given the element of the affine Y group, you can calculate a number in terms of the affine Hecke algebra, and you can show using kind of Lefschetz theory for these graphs that the conjecture is true if the characteristic is bigger than this number. And here I use that it's true in characteristic 0. So somehow I give an upper bound on these numbers that can occur as denominators for in the algorithm. So these two results are very hard to obtain. You need at the end the decomposition theorem and intersection cohomology and everything. But there is one instance of the conjecture which is very, very, very elementary which you can prove by very elementary methods. And this is the multiplicity 1 case. So we know that this is isomorphic to S if and only if the conjecture says so. So this is the multiplicity 1 case, and this you can prove just by looking very closely at the graph. The funny thing about this is that it also holds in positive characteristic, and for the applications to Lusztig conjecture, this gives its multiplicity 1 case for any field with characteristic bigger than the Coxeter number. And as far as I know, this is the only result that holds in full generality. So for any field which is with characteristic bigger than the Coxeter number. This gives a hint, at least, that the Coxeter number really is the right bound for Lusztig's conjecture. Okay. Let me use 5 minutes, maybe a little more, to give you an idea of how the first instance here is proven, how you prove this conjecture in characteristic 0. So, and there you need yet another quite different theory. Namely, here you need topology. The topology of the affine Schubert varieties. So, let us define the affine Fleck variety FL as a quotient of the loop group GT modulo the Ivahori subgroup so the Ivahori subgroup sits inside the disk group corresponding to G as follows. So if you evaluate, so you can think of this group as the group of maps from a small disk to the group, and you can evaluate this map at the center of the disk and get an element in the group. And the Ivahori subgroup is just a pre-image of a Borel subgroup. So these are infinite dimensional groups, and you have to work a little bit to define, well, not just a little bit. Pardon me?
The field.
Ah, right. Thank you. The field is the complex numbers now. So this is a topology associated to the complex group. Thank you. So you can define a topology on this space, and similarly you can define partial affine Fleck varieties where you divide out certain minimal parabolics. So these parabolics contain the Ivahori subgroup. So this situation comes with certain maps from FL to FLS, certain proper projection maps. And then there's a torus acting on these spaces, namely the extended affine torus. So this is the torus we started with, cross another copy of C star, which somehow, so this acts on the group, and the other copy of C star, it rotates the loops. In this situation, we can define the equivariant derived category of these two spaces. And we have two maps. So the push forward, let's call this pi s. And the pullback. And then we define the following. Here, this is the equivariant sheaf on the base point. Oh, no, I mean, sorry. It's here. It's the equivariant sheaf on the base point. A special sheaf is a direct sum of shifted direct summands of various sheaves that we sheaves that we obtain by pushing forward and pulling back in various ways our base sheaf. So, well, the only thing that somehow I wanted to explain here, without going into the details, is that you have a base field, base sheaf here, a certain unique, very easy object, and you have these kind of functors. And then what you do for any S, for any simple reflection, and what you do is you take your sheaf and you just apply all these functors in all the different directions to the sheaves, and then you take direct summands and then direct sums, and you get a certain subcategory of special sheaves here. So a theorem is that W hat parametrizes up to shifts the incomposable special sheaves so W to a W we associate a sheaf FW, and then you show that, second part of the theorem, that the following map, the localization map in equivariant cohomology from FW to the following direct sum so here Ix the inclusion of a fixed point this map, which is called a localization map, identifies with the following. It's the global sections of this BW inside the direct sum of its stalks. So the thing here is that there's a certain map coming from topology, from a certain localization theorem, and you can identify with the map that embeds the global sections of such a sheaf inside the direct sum of its stalks. And to be very precise, one should check here these B doubles. That means that here what we actually have to use is the topology associated to the Langlands dual group. So there's a Langlands duality here. But this is a theorem, and here you see you can read off, we have an identity here between these two spaces, and you prove this theorem using this identification because it is known that these local cohomologies, equivariant cohomologies, the rank of these spaces is given by an Effingham-Lusztig polynomial. So Lusztig and the decomposition theorem The theorem of Cauchy-Lusztig and the decomposition theorem says that the rank of these spaces is given by an affine Cauchy-Lusztig polynomial, and so this is the way how you can prove the main conjecture in characteristic 0. Okay. Well, maybe one more minute. There's a certain research program that I'm following, and it looks like this. Using these moment graphs that you see here, or Brugger graphs that you see here in the middle, you can connect various topological and representation theoretical categories, and all these solid arrows here are already established, but there are two arrows here to the critical affine category O and to the intersection cohomology sheaves on semi-infinite flat manifolds that are not yet established. And this is an open research project, the one I mentioned with Tomoyuki Arakawa. But you will see how these different theories, all associated to an affine Weyl group, are interconnected using sheaves and Brugger graph and the work of Anderson, Jensen, and Zergel using on the representation theory of the small quantum group and the representations of modular Lie algebras. Okay, so thank you very much.
Thank you very much. Are there questions, comments?
If you, so this BWX, the rank of BWX,
Yes.
can it be computed, say on a computer, or like
Yes.
Cauchy-Lusztig polynomial?
Yes. Yes, I currently have a student who wrote a computer program, and he tries to calculate using this algorithm of Braden McPherson all these BWX, and we hope to at the end to prove the Lusztig, I mean using computers to prove the Lusztig conjectures in the case A5. But somehow what we didn't expect is the following. Already in case A4, the graph that comes into the picture looks like this. And this is the case A4, and this is already very difficult for a computer. And A5 is very horrible. So we're not yet sure if we can actually compute all these sheaves that are for Lusztig's conjecture in the case A5. So these graphs get very difficult very soon.
Which Cox are you using P close to Coxeter number?
Well, he does it even over the integers. So he tries to calculate the Braden McPherson sheaf over the integers.
You don't need to know the sheaf, you just have to know the rank.
Yeah, but this is an inductive procedure. So so in order to calculate BWX, you have to know the sheaf on everything which is smaller than X.
Because the multiplicity one case is good, but it's actually a smooth case.
Yes, that's true. That's a smooth case. Yes.
So it's dangerous to draw conclusions about singular.
That's true. That's true. Yes. That's when I'm not sure if it's a strong support of Lusztig's conjecture or not so strong. I mean, the smooth case is not so. I mean, it's not so. There are not so many.
It would be
smooth
nice,
cases.
say, for SL4, say, for A4, you say, for A4, so in case of characteristics, something like 7.
Yes.
To actually see the comparisons of this.
Which comparisons? Which?
Well, to have some evidence that the random McPherson conjecture holds, say, for P equal 7, or
For A4?
yeah,
Or for
at least some singular examples where they
oh, yes,
actually
no, we are calculating the singular examples, and for A4, this graph, we can calculate everything with enough patience. but A5 we need maybe too much patience.
But you've seen some singular examples for small pieces.
Oh yes, they get highly singular very soon, these graphs.
I don't mean graphs, but yeah.
And well, it's in perfect accordance with Lusztig's conjecture, and also with what people conjecture for the affine Fleck manifold. So there you can look at sheaves with coefficients not in the complex numbers, but in positive characteristics. So the coefficients are in positive characteristic, and there it's also in perfect accordance with all this, actually, what people conjectured. So, but we calculate a lot of highly singular cases.
Standard duality that you have at the end, and you see it purely in terms of Keuler-Lusztig.
The Langlands duality. No, I mean, it's not a very deep fact, because I mean, the localization theorem describes this embedding in terms of a moment graph which is labeled by the roots for the group G. But here you see we had the co-roots as labels on the moment graph. And this is the only reason. So, I mean, you identify these two situations by showing that they just give the same sheaf on a certain moment graph, and you see the moment graphs coincide if you go to the Langlands dual side on the representation theory.
Other questions? Let's thank the speaker again.